So this is what's going to happen, that a carbocation intermediate is formed. And the bromine is going to steal away the electrons from this other carbon atom. The double bonded electrons over here, the bromine is going to come in and steal those. And in the next step, you'll have a Br minus one that's going to be attracted to the carbocation. It's going to bring its electrons and it's going to bond with it. So finally, the second bromine is also going to bond with it. So you've got these H atoms. And now you've got both bromines bonding to it. So is the mechanism clear?
Sir, what is this O and X in Br plus and Br minus?
That's the two electrons. I mean, you had bonded electrons, right, between the two bromine atoms. Okay? The two electrons got repelled because of the pi electron cloud over here, right? So this is the mechanism of the reaction. Now, one reason why this reaction happens is that if you look carefully, at least to the first part, if you look carefully, there's a pi electron cloud. Okay, let me draw the pi electron cloud. Okay, each carbon atom has a spare orbital and they're going to overlap. And they're going to overlap over here. So there is this pi electron cloud. Okay, and this pi electron cloud has a very high electron density. Okay, so there's lots of electrons over here. So it's got a high charge density. Because all the electrons are concentrated in this small region over here. I mean, the spare electron of carbon over here and the spare electron of carbon over here, they're going to overlap above and below. So the charge density is kind of concentrated. It's a very high charge density. So it's got very large polarizing power. So it's got this large polarizing power. So when a bromine molecule approaches it, due to the high negative charge density, the molecule is going to be polarized a lot. The electrons over here are going to get repelled. This side would be negative, this side would become positive. The positive will be attracted even more, and the negative is going to be repelled even more. So remember this point, that this pi electron cloud has really high charge density. Is this point clear?
Yeah.
Okay, so which is why it's able to polarize the bromine molecule on its own. You don't need any special conditions for this. The reaction happens at room temperature. So which is why no special conditions are needed in this case. You don't need any catalyst, you don't need anything for bromination to happen. So then we discuss the Markovnikov's rule as well. So what happens, let's also talk about the explanation for the Markovnikov's rule. So what happens in that scenario? Why is there a Markovnikov's rule to begin with? Why does H like to bond with the carbon atom that's already bonded to more H atoms? So let's talk about the mechanism for that reaction. So I've got a CH3 double bonded to, and I'm reacting it with HCl. Now, HCl is a molecule that's already polarized. So it's got a positive carbon atom, it's got a negative Cl atom. The electrons are going to be attracted to the positive carbon atom, and the electrons over here are going to get repelled. So it's already a polarized molecule. So in the next step, there are two options. The positive H is getting attracted, and the Cl-1 has been repelled with its electrons. So the positive H has two options. It can either take the electrons from the electron cloud and bond with this carbon atom. So if it does that, the H is going to take away the electrons in the double bond with it. The positive charge is going to disappear, and it's going to appear on this carbon atom because the H stole electrons from the double bond which belonged to this carbon atom. Or the other thing could happen. You could have another carbocation, which is now the other thing that could happen is that the H would come around and it would steal electrons from the double bond, take those electrons, the positive charge disappears, and this carbon becomes positively charged because this H took away or stole electrons that belonged to this carbon atom in the double bond. It took those electrons, and you got a Cl-1. So you get two carbocations getting formed. One of them is this one of them is this one. Is this clear?
Yeah.
So the rule is this one is your major product, and this one is your minor product, because according to the Markovnikov's rule, we studied that the H atom likes to bond with the carbon atom that's already bonded to more H atoms. Okay, so the H atom likes to bond with this carbon atom, not the other one. Okay, is that also clear that this is the major product?
Yes, sir.
अच्छा, अब issue ये कि if this is the major product, why is this the major product? Why is it easier to form this thing rather than this thing? Okay, this one is stable. I mean, anything that's easy to form that's stable. This one is unstable because it's very hard to actually form that. So this one is unstable. So you've got a stable carbocation, you've got an unstable carbocation. Now everything depends on this thing. It depends on the positive charge that's over here on this carbon atom. And it depends on the positive charge that's on this carbon atom. Now, one of those positive charges are not the same. This one has a small positive charge. This one has a large positive charge. I mean, they're both plus ones, but this one has a tiny positive charge. This one has a much, much larger positive charge. And the reason for that is that this positive charge over here is surrounded by electrons. There's a carbon over here, a carbon chain on this side and a carbon chain on this side. So it's surrounded by a bunch of electrons, right? I mean, if I show this, I got a carbon atom, there's a carbon chain on this side, and there's a carbon chain on this side. There's an H on this side, and here's your carbocation, right? So it's got carbon atoms on both sides, and carbon atoms have this electron donating effect. So this is what's going to happen. That carbocation has more alkyl chains. So it's got more alkyl chains, which are electron donating. So positive charge density decreases. So the positive charge density decreases on the carbocation. I mean, the positive charge over here decreases because it's surrounded by electrons. It's surrounded by large groups. So the electrons get pulled and the positive charge becomes smaller in size. Is this point clear that the positive charge is smaller in size? Is this clear?
Yes, sir.
Yes, sir.
So this one is larger in size because this is right at the end. It's got two hydrogen atoms around it. A hydrogen, they don't have electrons themselves, so they're not lots of large groups surrounding it. So the positive charge is not surrounded by electrons. I mean, over here the positive charge was right in the middle of the chain, so it was surrounded by electrons. So which is why the electrons got pulled and the positive charge kind of decreased. Over here the positive charge is large. There are fewer alkyl chains around it. So you got fewer alkyl chains. Around the carbocation. So there's going to be more higher charge density. So there's going to be higher charge density. Now the issue is, what difference does it make? Like this is small and this is big. ये तो पहले clear हो गया ना कि this one is small and this one is bigger in size. Is this clear?
Yes.
Yes, sir.
So now the question is, what difference does it make? The difference it makes is that this positive charge is large. Who was stealing electrons from it? It was this hydrogen that was stealing electrons from it. So if this positive charge is large, it will not allow the hydrogen to steal those electrons from it. And what it's going to do is it's going to pull those electrons back. Why would it allow the hydrogen to take away electrons? And it's going to pull those electrons back. And the hydrogen would not be able to take away those electrons from that carbon atom. Is this point clear?
Yes.
I mean, it was the double bonded electrons that were being pulled by the hydrogen atom, and hydrogen was bonding with them, which is why the hydrogen no longer had a positive charge, and the positive charge got transferred to the carbon atom over here because hydrogen stole those electrons. But the positive charge, and we're seeing that the positive charge is large. So if it's large, why is it giving those electrons? It's not going to give those electrons to hydrogen. So it would be very hard for hydrogen to actually take those electrons. So it would be very hard for the carbon atom to take, for the hydrogen atom to take this route. Over here, this is not the issue because if hydrogen comes along and steals those electrons in the double bond, the positive charge that will develop on the carbon atom is not going to be very large. It's going to be small. So it will kind of allow or encourage the hydrogen to steal those electrons. Is this clear?
Yeah.
So the thing is, the charge density decreases on the carbocation, and carbocation is going to be more stable. This is what you're going to write in the paper. About the carbocation that have more alkyl chains, which are electron donating, their positive charge density decreases, and the carbocation is considered to be more stable because this carbocation will not be fighting over electrons with this hydrogen atom. This carbocation, on the other hand, would be fighting over electrons with this hydrogen atom because it's not going to allow the hydrogen to take those electrons. So it would be very hard to form this carbocation. It would be a lot easier to form this carbocation. It will allow the hydrogen to steal those electrons because the positive charge is not big in the first place. Okay, is this clear, everyone?
Yeah.
Yes, sir.
So that's the Markovnikov's rule that why is this more stable? You just have to remember that carbocations that have more alkyl chains which are electron donating, their charge density decreases. And the carbocation, this one over here, is considered to be more stable, which is why this is more likely to be formed. So let's continue with this tomorrow then, okay?
Okay, sir.
Okay, everyone. Take care. Allah Hafiz.
Thank you.